Hi, welcome to the session on experiments with TensorFlow. Today we are going to look at building recurrent neural networks using TensorFlow 2.0. So let's break down the problem into multiple steps. Step 1, let's analyze the use case. So we are going to source the data from Kaggle. This data has about 57,650 songs rendered by different artists. We are going to pick a specific artist of our choice. And then we are going to crawl all the songs rendered by the artist. In the process, we'll do a certain set of cleanup activities. Once the cleanup activity is done, we are going to build a model. And then we are going to feed into the model a seed text. A seed text is just a certain set of words that will appear as the first words in the song. And then we expect the model to generate about 200 odd words from that particular sequence. Let's see how we can do that. So in the scenario that you're not familiar with recurrent neural networks, I have enclosed the respective playlist in the notebook. These playlists are from andrewngdeeplearning.ai course, and they will give you very good fundamentals on the concept of recurrent neural networks. Let's look at the step 2 now. The step 2 is about preparing the environment. Let's check the version of the TensorFlow which is installed in the current Google Colab. As you can see, it is currently 1.14, and this particular exercise was built on version 2.0. So I'm going to uninstall the current version of TensorFlow, and I'm going to install the GPU version of TensorFlow, which is 2.0, onto the system. Once done, I'm going to download the data which I have already uploaded to GitHub, and I'm going to unzip the data into the temporary folder of the Google Colab environment. A quick reference: before I start downloading the data, I'll import a specific set of libraries which we will articulate as and when this library is being referenced. And we are going to look at the artist by name Bruce Springsteen. He is a very popular artist, and I loved his rendering of Born in the USA. So I'm going to pick that particular artist for the current analysis. So let's onboard this particular data onto the pandas data frame. And then I'm going to filter the data by this particular artist which we had selected for analysis. And as you can see here, there are about 175 songs that has been sung by that particular artist, and which we will be using it to build our model. Now, what we are going to do is we are going to remove a certain set of stop words from this particular songs, because these stop words do not make any sense. So there are two types of stop words that I'm going to use: stop words and words to be removed. In essence, stop words are typically the single characters which do not make any sense in terms of bracket open, bracket closes, dot operators, colon operators, and so on and so forth. And then there are words like chorus, which does not make sense in the current scope of analysis, and I'm going to remove them from the current song list. So before I do that, what I'm going to do is I'm going to compile all the songs by that particular artist into one single object called data by artist. Now, data by artist is nothing but a list object which is going to contain all the songs sung by that particular artist. And then I'm going to store that particular entity into something called corpus. So as you can see here, I have referenced the first 10 lines. So it says, "We fell in love and I made you the world," and so on and so forth. So what I'm going to do is, as discussed earlier, I'm going to remove the specific words embedded in this particular song by iterating to the list object. And then I'm also going to replace the stop words, which are like singular characters which do not make sense in the context of our analysis. Once we do that, we are going to remove any leading or trailing characters from that particular string by using the strip command. And in the process, I'm also going to remove any empty elements so that we have the right lyrics being given as input. So at the end of all the cleaning process, the length of the corpus is about 5788, and that is what we are going to use for our analysis. Let's look at step 3, which is processing the data using TensorFlow. In this particular step, we are going to apply the tokenizer. Now, a quick example of what the tokenizer does. Let's take the sentence called Shyam is a good boy. When you apply the tokenizer on this particular line called Shyam is a good boy, it breaks the line into multiple words. The first word is Shyam, the second word is, the third word is a, the fourth word is good, and the fifth word is boy. And each of them is assigned a unique ID. So the job of the tokenizer is to break all the lines into respective words and assign each word a unique ID. And that's exactly what we are doing here. We are applying fit on text function on top of the corpus. In turn, it generates a dictionary called the word index. Now, word index is a dictionary which contains a key value pair, where key is the word and value is the number. As you can see here, there are about 4221 words in that particular corpus. Now, we are also going to create another dictionary called the reverse word index, which is nothing but a flip of the word index. Instead of having the key as the word, we want the key to be the numerical ID so that we can give a numerical ID and identify the respective word. So that is step 1 within the processing the data using TensorFlow. The next step is to create something called an Engram sequence. Now this may not make a lot of sense at this point in time, but bear with me. Very soon you'll be able to understand why we are doing Engram sequence. Now let's go back to the same example called Shyam is a good boy. Now there is sentence 1, which is like one sentence. Now we are going to create 4 more sentences like that. The first sentence is going to have the word Shyam is. The second sentence is going to be Shyam is a. The third sentence is going to be Shyam is a good. And the fourth sentence is going to be Shyam is a good boy. Jump into creating the Engram sequence. We need to apply something called text to sequences. And this text to sequence is applied on each and every line in the corpus. It does a very simple job. It assigns every word in that particular line an ID. So if you remember in the previous step, when we applied fit on text, it generated something called a word index. Now it uses that word index to fill in the respective ID for that particular word. So let's quickly run this particular command and let's have a look at what the text to sequences is. So when you say input sequence is 0:4, you can see that these are the sequences that are being generated. The actual sequence is 2730983774, and through Engram sequences it has been broken into multiple. So one line has become now 4 different lines. So the first sequence is 27309, the second sequence is 273098, the third sequence is 27309837, and which all represent some kind of word. Now let's use the reverse word index that we had built earlier, and let's find out what are these words, correct? And when you run it, you'll see that this represents something called we fell in love. And let's also have a look at the number of sequences that has been generated. So we have a sequence of 37,630 sequences that have been generated through the Engram sequence. Now, once we apply the Engram sequence, as you can see, each of those sequences have differing lengths and which is not homogeneous. So what we want to do is we want to make sure all these lines present in the sequence are of fixed length. So if you are thinking right, then what you would do is you would probably do a padding, and you would pad it based on the maximum length of that particular sequence. So we have a lot of lyrics, we have a lot of songs, and each song has different lines of different lengths. So we pick up the line which has the maximum length, and then what we do, we pad each line with that particular sequence. So what we are using is we are going to use something called pad sequences. Now pad sequences is a function within the TensorFlow library where you pass the input sequences and you give the maximum length. So in this case the maximum length is somewhere around 18, correct? So what we are going to do is we are going to run this particular step, and let's say we print it out. The maximum length of sequence is 18, and then what we are going to do is we are going to apply the pad sequences on top of the input sequences that we had already generated, giving the maximum length sequence, and we are going to say padding is equal to pre. Now when we do that and when we convert it into an array, what we get is some kind of an output, as you can see here. So each sequence now is of the same length. Now if you look at it from a comparative perspective, the earlier sequences had differing lengths, as you can see here. Now with the padded sequence, each sequence becomes of the same length, which is 18. So what we are doing is we are pre-padding with the number 0. Now I'm sure you might be asking, why are we doing pre-padding and not post-padding? So bear with me, we will come back to that very soon. So what we have here is a list of sequences which are of same length and they are pre-padded with 0. Now let's come to the most important part of why did we do pre-padding and why did we even create this Engram sequence. Now we are going to break the entire sequence that we have into X and Y's, where Y is the label that we are looking to predict. So if the word is V, we want to predict fell. If the word is V fell, then we want to predict in. If the word sequence is V fell in love or V fell in, then we want to predict love. So we want to learn based on the labels. So what we are going to do is we are going to assign the last column in this particular sequence as all the labels, and then all the rest of the information we are going to assign it to X. So we have got two parts, the X, which is a feature, and the Y, which is the label, and the label here is the last number, and that's why we had created something called the Engram sequence, and that's why we wanted to do a pre-padding so that we can isolate the labels. So what we are going to do here is we are going to create two new variables called the x's and the labels, where x's represents all the information, correct? In this particular case, x's represents all the data points till 27, and 309 becomes the label. And if you look at the next sequence, the 27309 becomes the X and the Y becomes the 8. So that we have defined the X and Y's, the features and the labels, we need to go one step further. We need to convert all the labels into something called one-hot encoding. So we'll use out of the box function toCategorical and then give labels as an input to the function, and then we'll also specify the number of classes. And if you remember here, the total number of words that we found out was about 4221, and that is going to be the number of classes that we are going to predict. So based on the entire corpus, we are going to predict one of those words to be the word which is going to come based on the seed text. So if I am going to say, if I'm going to give the C text as V fell in, then we need to calculate which is the next word that is going to come, most likely. So probably the love might be the word that might come after V fell in. So in order for us to do that, we are going to convert all the labels to one-not encoding, as you can see here, which I have already done. And then when you print out the YS, you will see a list of zeros marked by 1 at certain places. So for every sequence that you see here, there will be a 1 that has been marked. Now let's take the sequence of YS of 0 and let's find out where it has been marked as 1 using np.argmax, and it is going to give us a number. And then when we go to that particular YS of 0 and locate that particular location, we see that it has been marked by 1. And similarly, for every sequence that you see in this particular matrix, one of them will be turned as 1, and that's called one-not encoding. Let's move on to the step number 4. The step number 4 is about building the model. So here you can see there are two new concepts that are coming into play. One is embedding and the other is LSTM. Well, for both embedding and LSTM, I have shared the links in this particular notebook, which will give you a very good introduction to both embedding and LSTM. At this point in time, we'll just assume that it works and then we'll move forward. So the two new parameters that I'm going to put in place, which is called the embedding size and the node count. So as you can see, the first layer in the neural network is the embedding layer. And the embedding has to be generated for the total words, which is about 4221 words. And the size of embedding has also been specified. And the input length is the maximum length of the particular sequence, followed by a few LSTM layers with return sequence is equal to true, followed by a dense layer having activation as relu, and the final layer being the softmax. If you remember, we need to predict what is the likely word that is going to come after a specific sequence. For example, we fell in, the most likely word that is going to come in is love. So this dense layer is going to give us the actual word that is going to be predicted for that particular sequence. So we are going to compile the model with the loss of categorical cross entropy and optimizer Adam. And as you can see here, there are about 22 million parameters that needs to be trained. And model.summary gives you all the details that is being layered in that particular neural network. Now, a quick embedding analysis. Once you run that particular model.compile, it is going to give you a certain understanding of what is embedding. So I'm going to pick the layer number 0, which is the embedding layer, and I'm going to get the weights, correct? And then I'm going to get the shape of the weights, correct? And I'm also going to initialize word index, correct? The word index is a separate data structure. And let's look at the word called happy, assuming that happy is within the particular layer. So the word index of happy will give you the key for that particular word, which is happy key. And then when I put it, the reverse word index is just an opposite of it, so doesn't make a lot of sense here, but just for the sake of understanding, I have put it here. So this gives you the key for the happy and also gives you the embedding size of that particular happy. So you could remove the dot shape and then see for yourself what does it mean by happy embeddings. And let's take another word called glad and let's repeat the same sequence. So in essence, embedding is a way to get the dense vector for each and every word, and that is pre-built inside this particular framework. So I have given a few more examples as well, which is just for your understanding, correct? And once you do that, you go and fit the model on the x's and the y's. So far we have constructed the architecture. We started off with an embedding layer, put a couple of LSTM with return sequences. We defined a fully connected network, and then we defined a softmax layer. Now, having defined that architecture, we are going to use that architecture to train on the x's and the y's. So x's is all the features and y's is nothing but the labels. And we are going to train for 100 epochs. So when you run this, as you can see here, when you run this, you get, for every epoch, it is going to give you the accuracy and the loss. And as you can see here, I have run this particular model.fit for a couple of iterations. So I started off with 50 epochs, and then I saw that accuracy went up to a certain point, and then I wanted to rerun the entire model for a few more epochs. So essentially, when I rerun this particular statement model.fit without rerunning the earlier steps, it starts from the point it stopped earlier. So when it stopped, it had an accuracy of 0.8216 at the end of the 50th epoch. Correct. From the 51st epoch, when I'm going to run it, it is going to start from where it stopped. So that's the beauty. So you don't really have to start from the beginning again. So later, if you want to change, if you change your mind, hey, you don't want to run for 50 epochs, but you want to run for 100 epochs. So I would suggest you run for 100 epochs and then see how the accuracy starts to build up, correct? Starts to increase through every iteration. And as you can see here, I'll plot the epochs and the accuracy. And as you can see here, it starts off at a very lower accuracy, and as the number of epochs goes on increasing, your accuracy also starts to increase, and your accuracy starts to plateau at a certain point in time, and which I observed too. Correct. So the accuracy that I hit at the 50th epoch, I had very marginal improvement after that till the 100th epoch. Very marginal improvement. So a couple of things that you might want to try at your end is probably you might want to use a different ordering of the neural network. So you have an embedding, you might want to have an embedding, and you might want to have a flatten, and then you might want to have a softmax layer. So play around with the different neural network layers, and that will give you a definitive understanding of how and what improvement happens. So once this is done, I'm going to go and use the seed text to predict the next 200 words. So what I'm going to do is I'm going to use the seed text called VLOUD, and then I'm going to, so what I've done additionally is I don't want to stick to a standard length for every line in that particular song. So what I did is I went and found out what is the average length of any song, correct? Average length of a line of any song. So if the artist has written about 175 songs, I picked the minimum of it, correct? And then for each line, I wanted to understand the average number of words in that particular songs rendered by the artist. So because I don't want to have a constant number of words across the lines, kind of making it more realistic. Okay. So what I've done is I've found out the average number of words per song, correct, and the average number of words per line. I'm going to take that, both of them, into account, and I'm going to use seed text called VLOUD. I'm going to, the first thing that I'm going to do is I'm going to do text to sequences. Remember that we did the text to sequences, which is going to break the word, the sequence into numbers. It converts the sequence into numbers because we already did on fit on text, correct? So we don't really need to understand what are those numbers, which has already been defined. So now we apply text to sequences, and then I'm going to apply the patch sequences. So these two are important steps for the seed text. and I'm going to do pre-padding, and then I'm going to do the predict. I'm going to identify what is the predicted word, and then the predicted word is going to give me something. The predicted data point which is going to come through is going to give me a number, and using the word index.items I'm going to identify what word does that number belong to, or sorry, the what number does that word belong to. So I'm going to identify the word, and then I'm going to concatenate that word to the seed text. So the first time I'm going to run it, I'm going to have we loved. The next time I'm going to run it, it's going to have we loved what. And the next time, the next iteration is going to run, it is going to say we loved what she can. So on and so forth, correct? So it is going to build up for every sequence that I'm going to give it as an input. It is going to find out the next best word that is going to be predicted. Now play around with this to have a better understanding, correct? And then what I'm going to do is, if you remember, we found out the average number of words per line. So I am not going to go beyond anywhere beyond 17 lines. So what I'm going to do, I'm going to say, okay, choose the average number of words for each line. So the first line that I found out is, we loved what she can just make it, to the morning to end up for gold, from the great beyond, from the other side, your other side of your leash light where the dry shells down. So as you can see, the entire sequence has been generated. Now if you had stopped training for about, say, around 20 epochs or 30 epochs, what you will observe is a lot of words are repetitive. So you'll find a lot of words that are being repeated. You can try it out on your own. So what I would suggest is, you don't do the entire training for 100 epochs, you do only training for 20 epochs, and then you do the prediction for the next 200 words, and you'll see a lot of words that come as prediction are going to be a lot of repeat. So since we had trained for a lot more epochs, which is 100 epochs, and we did reach an accuracy of 0.82, and which kind of plateaued at that point in time because there was no way it increased more, correct? Probably with a different neural network architecture you might see a better improvement, and then you start to predict what is the next best word that can come given that particular sequence. Again, I'm not very sure whether a lot of those sentences make sense, but then at least the first sentence, we loved what she can just make it, probably makes a lot of sense, and then so on and so forth, correct? Some of them might not make a lot of sense because probably you need a lot more training data set, correct? Not just 175 songs, probably you need a lot more training data set for you to have a perfect lyrics that could be generated for that particular artist. But then this is the first try, and I'm happy with what I have achieved. So you might want to try on your own for a different artist. Let's say you want to try Katy Perry or somebody else who you like, and see whether the lyrics that get generated mirror what the artist generally sings about. And that's very particular. If you were to mash up all the lyrics, for example, I mash up the lyrics of Eminem and Bruce Springsteen, I might get something very surprising which probably Bruce Springsteen would never have rendered as a song. So those are some of the interesting things that you could try in terms of this, correct? To have to make it more fun in terms of what your learning is. So thank you for listening to this particular session. So do share your views and do share your experiments and see, and also let me know what you did right for you to get a more great set of lyrics that you have generated to your end. Thank you again.